Today we're going to be talking about exploit prediction and effective prioritization. So this was largely what most people in vulnerability management were dealing with this year. Meltdown inspector, side channel attacks. I think in talking with folks over the last 6 months, life has been pretty challenging because they're being asked these questions. What are we doing about this? How are we managing this? Should we fix this? And in some cases, the answer is yes. In many cases, the answer is no. And why is that? You can't, we're not going to fix all of this. There's complexity in the stack. There's a ton of stuff affected. And it's not just patches. You actually have to go patch the microcode. So, should we fix it? Well, it depends. And this is kind of what the modern day server looks like. And at every layer, there's a lot of work. So should we patch it? Yeah, I mean, if we have time, we should patch it. Do we have time? And it really comes down to time. And in addition to that, 2017, 2018 was challenging. There was a lot more vulnerabilities named and numbered, which is a good thing. We should name and number our vulnerabilities when they're found. But that spike is going to stick around. And the reason for that is because MITRE went out and distributed the workload. They went to they set up CNAs. Everybody knows what a CNA is? Does anybody know what a CNA is? I got one hand. OK, cool. A CNA is a certified numbering authority or a CVE naming authority. And they can actually work with a researcher to name a vulnerability, to put it into the MITRE database, and make it an official CVE. Well, that's a good thing, right? In 2016, we didn't have enough bandwidth at MITRE to be able to name these things, and so vulnerabilities were getting, they weren't being named. So we didn't know if it existed or not. Now, we're actually naming those things. We're actually knowing that they exist in a given product, a given stack. That's good, but there's more work. And at the same time, and this is work that we did at Kenna with Scientia Group to figure out, OK, realistically, how much time do we have? And you can see, based on this, that exploits being released into the wild happens very quickly. It happens within a 2-week window around the CVE being published on average. It's crazy, right? An exploit being released into the wild means that there's more risk associated with a given vulnerability. And so you should interpret this as the time window is it's small, and in fact, it's getting smaller for us to be able to patch in time of preventing a given vulnerability from being exploited. But there is good news. And the good news largely boils down to there's a small subset of vulnerabilities that actually matter. And which ones matter is part of what we're going to talk about today. And that small part is actually 2%. That's good. For that big increase in CVEs being named, there's only a few that actually matter for getting patched in time. So how do we find and fix these before we have an event on a given vulnerability?
So a lot of what Cran's talking about here is an increase in the amount of data points we have to deal with, an increase in the speed with which attackers are exploiting vulnerabilities, and a lack of a way for us to make decisions. So most of this talk is all about how do we make people who are responsible for remediating vulnerabilities make decisions that are smart and effective by presenting them with the right types of data. This is a paper that I wrote about 6 months ago, and it talks about how we should be training these models that we have in security. Most of what we've been doing in security for the past 20 years or so is creating a lot of sensor networks and creating a lot of data so that we can identify vulnerabilities. In fact, that last chart that you saw with the increase in 2018 in vulnerability disclosures and the new CNAs is another consequence of that. Even our national vulnerability naming databases are now thinking about ways to create more vulnerabilities, to record more vulnerabilities, to create more data. But the problem that we haven't been so good at thinking about is how do we create signal from that data so that decisions are made accurately and that they're made effectively. This talk is going to be two sections, really. One is going to be about how do we think about not have we fixed the right thing, but are we employing the right strategy so that over time everybody in our organization is effective with their remediation policies, but also is capturing all of the threats that are out there. And the second piece of the talk, we'll walk through a model that does that and talk about how it can be useful, what the future work is, where we need to be going. In this paper, there are a couple of takeaways. The first is that there's a lot of data insecurity, but we're very bad at discerning signal. A lot of the reason that we all have our jobs is because we can look at data and we can discern signal, but there's just too much of it now and there's not enough security professionals. So the correct response to it is to cost effectively test it. So if you think about the typical IDS problem, you want to throw away a lot of false positive alerts really quickly so that you're not looking through every single alert. The same is becoming more and more true in vulnerability management. And we'll talk about how to increase the amount of time you spend thinking about Spectre and Meltdown without missing a lot of threats. So I'm going to walk through three small pieces of data, but each one of these is illustrating a larger point. The larger points here are that the dogma that we use to think about vulnerabilities today isn't justified in the data, and the reasons why those justifications fail is how we're going to construct that model. So here you're looking at all of the vulnerabilities in the National Vulnerability Database, and the most interesting thing here is that of the vulnerabilities that are never attacked, about 88% of them are scored highly. And so what that means is that if you are remediating only high-ranked vulnerabilities, and many organizations still have this policy of highs and criticals on CVSS is what we remediate, you're wasting a lot of effort. Or rather, you're remediating vulnerabilities that are not necessarily the ones that attackers are going after today and that aren't the ones that create exposure to your business. If that's true, then that policy of scoring those vulnerabilities highly isn't what's incorrect. What's incorrect is not being efficient with your time of remediation because you know you have limited resources. And keep that in mind, this is going to build an intuition towards a larger thing we'll talk about, which is how to be effective while not missing any threats. Another interesting piece is that in 2018, of all the vulnerabilities that were successfully attacked in 2018 so far, only 36 were published in 2018. About 630 were attacked successfully in 2018 to the best of our knowledge, but only 5% of the ones that were attacked were published in 2018. So if your policy is let's jump on every patch Tuesday, make sure we're really up to date and remediate every new release and make sure we don't have any new vulnerabilities, that might not be such a smart strategy either, because then you're missing 95% of the threats that are still out there affecting your business every day that were published in 2014, 2015. In fact, I think the most exploited vulnerability we found in our data set for 2018 was from 2017. So that tells you that recency isn't a good heuristic either, but the reason recency isn't a good heuristic is completely different than that first reason. It's that by pursuing the most recent vulnerabilities, you might capture some, your time might not be wasted, but you would be missing a lot of the threats that are still out there. So you want to be effective with your time, but you also want to make sure that you're covering all of the threats that we know about to the best of our data. And then another interesting thing occurs, which is if you look at the timeline for exploitation from the release of the vulnerability or the publication of the vulnerability to the time it was first exploited, to the time we first saw an exploitation event related to that vulnerability, then in the overall picture, the very bottom line, it's all over the place. Sometimes the release, you see an exploitation before the release, sometimes it's on the day of release. The median is somewhere around 55 days, but really the spread is everywhere. Once you break it down by products, though, you start to see some new information emerge. And what's more interesting here than the information I'm going to tell you is that this breakdown is valuable because we see separation. So when you look at Mozilla and Apple, you know that those vulnerabilities take longer from release to exploitation. You don't naturally see exploited in the wild vulnerabilities that are Apple vulnerabilities. Maybe people don't want to burn those 0 days. Maybe those vulnerabilities are just harder to exploit. Maybe they don't disclose as many. But this can be a guidance for your policy. However, if you drop down and look at Microsoft, which is the remainder of this, it's also all over the place. So what that tells me is we need more data. We need to look more granularly at Microsoft vulnerabilities in order to generate the kind of separation we're seeing here. And so even if you have a policy that seems like an effective slice at the first glance, like I know what's critical, I'm going to fix only these criticals. And even if you know that your policy is real-time and dynamic, it doesn't just look at the newest vulnerabilities released today, that still might not be enough granularity in your data. You need more in order to be able to set a policy for every vulnerability specifically. And so what are these things that we want to look at? What are the features of vulnerabilities that do get us to more efficiency and more coverage? And this is how I want everybody to think about every other slide we present. We want you to think about it in terms of, is the data that we're presenting, the information that we're presenting, or the model that we're presenting, can it make my organization more efficient with our time to be able to target only the threats that are being exploited, while also making sure that we're not missing anything and we're not ignoring any of the threats that we know are out there? So you can think about, have we seen somebody else have a successful event? We can think about, how do we detect success? Is there a signature that's written for this vulnerability or not? Is there an exploit that's written for this vulnerability or not? We can think about, what does the attacker get if they exploit that vulnerability? And can this be accessed in our boxes? All of these are how we build our scoring systems internally, but all of these are actually not data-driven. They're more or less intuitive things about the process of vulnerability exploitation rather than things that we uncover with the data. However, we confirm them with the data, and the data itself tells us specifically which vulnerabilities we want to fix. We'll get to that at the second half of the talk where we talk about some specific ones too. We skipped a slide there, but that's okay. Cool. So how do we know if we're working on the right stuff is really important, because everything we've talked about now, the data is only available, or I'm only able to show you those charts and talk about efficiency and coverage because we have two data sets. We have a data set of vulnerabilities, which for Kenna security today looks like 13 million assets, close to 3 billion vulnerabilities across hundreds of organizations. But we pair that up with data from events, which can come from a piece of malware being reversed by reversing labs that was submitted by somebody. It can come from an IDS signature trigger in an Alien Vault OSIM box. It can come from proof point emerging threats, knowing that there was an attack launched. All of those events have nothing to do with vulnerability management, or so you think. They're all about the detect and response side. And the takeaway from looking at that data is that you can analyze how effective a strategy is on the prevention side, on the remediation side, by looking at its impact on the detection side. So we use the number of successful exploitations. We use the kinds of vulnerabilities that have exploits or are exploited, which is traditionally a function of detection, response, investigation, to measure how effective the strategy that we're building are. And I'll let Cran talk about how exactly we do that.
Cool. So what Michael's saying is really only retroactively do we understand if we worked on the right stuff, right? The patch windows exist, time is a problem, and so knowing early what we need to fix in order to have enough time to fix it is the challenge here. So we really we look at two concepts. We look at coverage, which we define as, of the vulnerabilities we fixed, did we pick the correct ones looking backward, right? And we would only know that now for stuff that was a problem 6 months ago, or we had enough time to fix it 6 months ago. And efficiency, of the ones we fixed, were those the right ones? And so this is easily explained through an analogy, which Jay, I'll credit Jay with this analogy. Imagine you have a robot lawnmower. Has anybody seen these things? They're great. They're fantastic. I want one. Imagine that you stick it in your yard and you tell it to go mow the yard. And you have a neighbor, and the neighbor's lawn happens to need mowing too. But you just toss it out and see what happens. Did it hit 100% coverage? Well, did it get all of your yard? In this case, no. And how efficient was it? Did it mow part of your neighbor's yard, right? If it did, then it's, that's inefficiency. That's wasted effort largely. So ideally, you want a robot that's smart enough to measure only your yard and cut it, and nothing else, right? And the same thing applies with vulnerability management. You really want to be able to fix only the stuff that's going to matter, but you're only going to know that in retrospect. You'll never know at time. So, imagine that this gray box here is all of the CVEs that exist, and imagine the red ones are ones with known exploits or events. And then imagine that you apply a strategy, and you look back 6 months ago, and some of those were exploited or had a public exploit that existed, and some of those were not. We would call this strategy very inefficient, right? Why? There's a lot of stuff we fixed, we applied effort to it, and it didn't matter. Like, nobody ever tried to mess with it. So I think the goal that we should take away from this is the goal is to patch only stuff that matters and nothing else. And we can measure that based on coverage. Did we get all the things that we wanted to? And efficiency, did we apply effort where we didn't need to? These concepts will be important further on. There's a natural trade-off. Every time you fix something, You don't really know where it's going to end up. So should you take an abundance of caution and fix more things, or should you try to limit your effort and, apply it only where it matters, where you know it matters now based on limited information? And the reality of this is incomplete information at any moment, right? And information changes over time. So your robot lawnmower analogy breaks down now because guess what? You now need to mow the neighbor's yard, or you need to mow certain patches of the neighbor's yard. So, but why would you want 100% coverage or less than 100% coverage? Maybe something that you needed to fix 6 months ago no longer matters when you actually get to it. Coverage and efficiency. But how do we handle these things that are moving quickly, and how do we make sure that we have enough of a window to be able to fix those? In looking at the data, and Michael mentioned this earlier, from published to exploit in 2018, of 639 exploits that were published in 2018 for 2018 CVEs, we have about 20 days. It's a pretty short window. And in fact, from published to event, we have about 30 days. The shortest window being Adobe Reader, no surprise there, I suspect. The longest window being Edge, which was months. And what are those popular targets? There's probably no surprises in this. These are CVEs that pop up in the various threat feeds that we have as escalating threats, things that are a standard deviation above a day or a week ago. And I suspect amongst this room, there are very few folks surprised by this list.
There's a couple interesting threads in what Cran's talking about. The first is that it was probably okay to just say we're going to fix these highs and criticals in a world where no real-time event data existed. Today, a lot of vendors have APIs. A lot of the threat intelligence feeds we have are more real-time, and we can find information about how to measure whether or not those assignments of critical, high, or medium were actually correct. We can do that kind of retrospective analysis that we do with the mowing of the lawn in real time, which allows us to make smarter decisions in real time. But it also allows us to evaluate whether or not those classifications, whether it's CVSS or some P1, P2 severity levels, whether those were correct in the first place. And you don't have to wait 6 months anymore because the data is coming in real time. And what are we really trying to describe with this data? Well, this is one example of how a vulnerability gets birthed in this world. Sometimes a vulnerability is created because somebody at Microsoft found that there's a vulnerability. They discover it, then they disclose the vulnerability. It gets published by National Vulnerability Database, and a scanner will write a detection for it, find it in a bunch of enterprise environments. Somebody will write some exploit code for it, and then eventually we'll see somebody using that exploit code, so maybe you should be fixing it now and worrying about it. But the reality is that none of these things are in order. Sometimes we find vulnerabilities only because somebody exploited it in the wild, and then Microsoft scrambles to write that up and publish it, and you won't even know about it until the exploitations are live. Sometimes public exploit code might be how we find out that the vulnerability exists in the first place, but nobody's using it yet. Maybe it wasn't weaponized, maybe it doesn't work that well, maybe it needs some modifications. Maybe it's one of these academic proof of concepts. There was one for Apache struts a couple of months after the initial one that is being used frequently, where people freaked out and thought, oh no, there's a POC exploit code, but it was academic, it didn't work, and nobody ended up writing exploit code for it. The shifting of all of these is totally okay as long as you've got instrumentation to measure which vulnerabilities have exploit code, which vulnerabilities are actually being used, and as long as you're getting the information about which ones are possible to detect versus which ones are being detected in your enterprise in somewhat real-time fashion. So what's interesting here is, why do we need to be all that fast about it? I mean, the truth is that most organizations have millions of vulnerabilities that are security debt incurred through old machines, legacy systems, things that have 24/7 uptime that you can't patch, or maybe just negligence. If we have this backlog of 2 million vulnerabilities, why do we care so much about the new things that come out? Why do we need to be real time? And the reason is that increasingly over time, vulnerabilities are being exploited faster after their publication date. Some vulnerabilities are exploited within days, minutes, or even before their publication date, because that's how we know about their existence. Some vulnerabilities can get exploited a year, 2 years out after their publication date. But what's interesting to see is that year over year, that gap is shrinking. And what's also interesting to note is that you're looking here at a probability distribution. And so even at day 1, there's some chance that a vulnerability released yesterday is going to get exploited. At day 2, that chance grows. At day 30, that chance is already really high. And so that area under the curve, all of those days multiplied by all of those probabilities, is the risk that we're trying to remediate. Because if we can be faster at identifying which ones we're going to be exploited or will have exploit code written about them, we can save a lot of that probability from being a risk that we think about at the enterprise. And that's what we're going to try to do for the rest of the talk. We're going to try to build a model that incidentally becomes both useful in predicting which vulnerabilities will have exploits published in the future, but also describes all of that security backlog and gives you a kind of natural way to prioritize between those vulnerabilities that do pose a risk to your environment and don't. Oh, this is also interesting. So this is essentially saying a CVE is assigned doesn't mean it gets published. Actually, the NVD has about 21,000 vulnerabilities that were assigned but haven't been written up yet. And so we know that a vulnerability is going to come out, or maybe a vendor has said, hey, we found a vulnerability in this. And then the uncertainty begins. We might know a description of it. We might know nothing else about it. Is it being exploited? Is there a signature for it? Does my scanner even know about it?
There's not even enough information to make a decision yet at this point, really. I mean, like this is incredibly interesting to me because it's like, it's saying as soon as we have a name, and we might have a description, we should have a description at this point. We don't have CVSS, we don't have any sort of attributes, we don't have an attack path that we know works. We just know that a vulnerability exists. Like, there's not enough information to make a decision. So we have to be able to make decisions in these limited information environments. How do we do that?
Yeah, we found with customers that there's two types of decisions that people want to be able to make. The first is this a threat? Yes, I should remediate it. But just as valuable is a decision of, we don't know anything about this thing, does it matter? If you can, in a data-driven, quantitative way, say the probability that you should care about it is low, then that alone is a valuable decision because it saves people cycles of thinking about it, revisiting it, or trying to write that exploit code. So let's talk about how we predict it. Essentially, we've been very good up to now at answering the question of we have a backlog of vulnerabilities, which ones should we be remediating? And the answer to that is stable vulnerabilities with known exploits that do work, that have high volume and velocity on products that we know are prevalent, where attackers can see high payoff. And data exists about every one of the little things that I just said, and most of that data is actually public, and you can guess which exploits you should be remediating. The prioritization of those, the granular prioritization, is a completely different piece. But what's missing from all of that is exactly what we're talking about now, which is even if you've addressed all your backlog, a new vulnerability comes out, you're faced with two decisions. The first is, do I care about the future risk that that vulnerability might incur? And how does that risk trade off with the legacy security debt that I have to address? And how do I generate new data about that vulnerability without somebody giving it to me? And this is why we care about machine learning in the first place. I'll jump back to this, but essentially, machine learning is a method for doing two things. It's about segmenting data or creating new data based on existing data. And what we're trying to do here is create new data, automatically recognize patterns in our vulnerabilities that are exploited, so that we can create data about those where we don't know whether it's exploited or not, whether it will be exploited or not. We want to measure the success of whatever model we build, not based on whether it's an accurate model, whether it does a good job, or whether we pat it on the head, but we want to measure it about whether or not it can raise the efficiency and coverage, not even of itself, but rather of the overall vulnerability management practice that we have. Because it doesn't exist in the abstract, this is just one of the many inputs that we have into a model that is a security strategy for remediation. We know that CVSS might not be a good one. We're trying to build one that has a good level of coverage while maintaining a high level of efficiency. What we care about when we predict exploitation about vulnerabilities or we create new data that we're not sure about is, can it help us be more efficient? Can it increase our coverage over time? And if it's fed into that strategy and increases any of those metrics, we know that it was a valuable model to build. So let me jump back here and talk about the sources. Essentially, we have a lot of CVE data or data about vulnerabilities coming from NVD, MITRE, CVSS, CPE. All of that is about products, vendors. It's all about which vulnerabilities we know about today, maybe even if we don't know that much data about them. And they're getting very good at adding new CNAs, numbering authorities, that are recording new vulnerabilities over time. The issue is that those sources are recording the existence of the vulnerability, but not a way to make decisions about them. In fact, if you look at the CVSS version 2 page, they'll tell you right away, this is not a standard for prioritization. This is rather a bunch of attributes which describe the model, the variable which you can use to build prioritization models. And so it's our job to get the data that does describe how risky those vulnerabilities are. And for us, that data comes from a bunch of places. The most interesting ones are Alien Vault's OSIM. So we tap into their freemium product, and we look at all of the vulnerabilities that have IDS detections on them that also at the same time the box where the detection happened had an open vulnerability matching that signature. That to us is an event. That event is indicative of exploitation. Maybe nothing happened. Maybe it was the Podbelly's lunch menu sitting on a box somewhere and the person got the Podbelly's lunch menu, so that's not a compromise event. But the fact that it was used in a technical sense successfully is indicative of higher risk because it could be used in a box that had credentials instead of PDF lunch menus. We get it from reversing labs. We OEM the data from all of the reversals that happen through the A1000 product, and then we know whether or not a piece of malware was reversed and matched a particular exploit or CVE that got it in there, and we know at what time that happened and the volume and velocity with when it happened. And then we get it from proof points emerging threats. So it's an email tap that looks at the number of signatures that are hit on different CVEs. Those are the actively exploited in the wild data sources. And then the rest are all about, do exploits exist for these vulnerabilities? That's Contagio, Exploit DB, Metasploit, Exodus Intelligence, the Canvas system. All of those will tell you whether or not there's the potential for exploitation. And all of that data is what we use to then train a model, which will tell us whether a new vulnerability that just entered the universe today has the potential or has a high probability of being exploited. So constructing the question that we ask the machine learning model is maybe as important as gathering all of the data. So we could ask, do I care about this vulnerability? And construct a bunch of measures about things we care about and don't, and create a multi-tier model that will then tell us 5 different outputs. But the more granular the question you ask, the less confidence you have in the answer. And so what we're building here is a classification model that just wants to answer one question about a vulnerability when it's released. Will this vulnerability have an exploit published in the future? Yes or no? Making the question that simple is what allows us to have a more accurate model and use all of the data that we have available in order to build that model. So today we're really good at saying, I have 300 million vulnerabilities, which one should I remediate? We want to get really good at supervised classification. I know nothing about this vulnerability. Is this one a threat to me or not? And the question that we're going to ask is, will this vulnerability have an exploit written for it? It will cause more risk later, so we can use that data point to integrate it into our overall decision-making process and hopefully have an efficiency and coverage lift. So these are all the variables that we have available to us based on the data sources that I talked before. You can look at them now, you can look at them later, but essentially there's a couple of classes here. Some of them are about timelines to exploitation or data about exploitation. Some of them are about timelines of exploits being written. A lot of them are about the Kenna security customer data, which is this a target that's popular? Is this something that a lot of our customers have? Is this a product that's prevalent? And then a lot of them are descriptions of vulnerabilities. So it's interesting to note that the categorical ones mostly come from CVSS, like authentication, access complexity, access vector. Those are just text-based variables that you mine out of a description of a vulnerability. It's just that NVD does that for us. So they categorize it into high, medium, low. They look at the description of the vulnerability and somebody makes that decision. But the great insight that you have about CVE text is that there's hundreds of other variables that you could be looking at in that text that aren't accounted for by CVSS that also could build a very good model. And that comes from descriptions, summaries, getting data from IBM X-Force and sources like that, and getting more accurate descriptions of those vulnerabilities. So let's set some expectations before I show you the models. You know, only about 23%, I think 22% now, of vulnerabilities have exploits on them. And so that means the data set is very unbalanced. If the data set was 99% unbalanced, you can think about it as you've got 100 machines, one of them is constantly infected, and every day I wake up and I go to the CISO and I say, nothing's infected. Then I'm right 99% of the time. My accuracy is 99%. All that says is that accuracy is not a very good metric. Instead, we default to precision and recall, which are measures of efficiency for precision and recall for coverage. For these models, for ones that are predictive, that create new data that we're not absolutely sure about, we care about the precision more than the recall. And the reason is we're not using it in the abstract. We're feeding into another model. We're giving it to a customer to make their own decision about whether they should prioritize a new vulnerability that we're making an estimation about versus an old one that is stable that we do have data about or maybe don't have data about for 2 years. And there, you don't want anybody to waste effort. You don't want them to make an incorrect decision because we're biased towards capturing as many of the future as possible while not being very accurate about it. And then another interesting thing to note is that we're not modeling the time. We will eventually in the future model when that vulnerability will be exploited. But what we're modeling right now is just if that will happen. And what's also interesting is that because we're running it daily and our data is updating daily, that confidence in the decision that we're giving the customer, whether or not it will be exploited, is constantly being updated and updated in real time. So as new data sources come in, as new classes of vulnerabilities might get exploited, the output will change. The confidence in the decision might also change. So the model doesn't exist in the static ways I'm going to present it today. It actually changes day over day and is dynamic, but we're going to assess it in a static way. Like Cran mentioned, there's a trade-off between precision and recall. If you wanted to remediate, if you wanted to capture all of the vulnerabilities that would ever get exploited in the future, all I would have to do to accomplish that is to say, look, you should remediate everything that gets released all the time. But that's costly, and that's not feasible, and that's not tractable. So the trade-off is that we can't capture everything. We need to create a model that is good at identifying just those things that will be exploited while not losing a lot of the coverage or a lot of the recall. And so here you can see the first stab at it. This is a model, a bunch of models created by Jay Jacobs at Scientia. And all of these, the orange model is the everything model, which uses all of the variables we talked about and more that are mined out of the text descriptions. But the ones underneath are really interesting. The blue one is based only on CVSS. So if you were to build the best model you could off of CVSS to try to predict whether or not a vulnerability will be exploited, if you had the CVSS score, subsetted on that data, then the best that that model would do is it would have about 40% coverage and 40% efficiency. If you build that same model only looking at the products that the vulnerability affected, you would get a slightly worse model, but it would get better towards higher levels of coverage. If you did the exact same thing with reference lists or the words in the descriptions, you could build much better models, which is also an interesting point by itself. This goes to say CVSS is mining out some of the text-based descriptions, not all of them. There's more involved in the descriptions than what CVSS is currently capturing. But if you created a model based off of everything, you start to arrive at a reasonable strategy that says, if I want 20% coverage, I can expect to be 85% efficient. If I want 80% coverage, I can expect to be 50% efficient with my time. And that is valuable first because it's continuous. It allows you to choose a decision point, a risk tolerance, a coverage tolerance, and know how much effort you need to get there, which is something that's very hard to estimate today. But it also allows you to classify new vulnerabilities using the scoring outputs of these. So here are the three models, and I'm just going to show you one of them. So this is we present three thresholds of the data. So we let the customer decide how much confidence they want in that prediction. But essentially, the model that we have today running in production is based in Amazon machine learning. It's a binary classifier. It will look at a vulnerability and assign a score to it. And anything that's above a certain threshold, we will say is most likely to be exploited. And what we mean by that is that the precision or the efficiency of that prediction is 95%, and we will be confidently capture about 20% of the vulnerabilities that will be exploited in the future. Keep in mind this reruns all the time, so every given day we're capturing hopefully more of it if we're getting more data. But that way we have a variable on each new vulnerability that says we are 95% confident this one will or won't get exploited. And everything where we're not that confident, you can safely ignore to focus on the security backlog, which is what Cran's going to talk about, as in how do you use a model like this versus just think about it in an academic black box.
Yep. So what Michael's talking about is you know, where does the rubber hit the road in terms of what it predicts? And if you look at how we look at the output, we end up with a list of CVEs with a confidence or really a number associated with it that gives us the ability to say this one is higher than this, a relative ranking. And you know, the things that show up near the top of this, arbitrary code execution, command injection, remote attackers, like those are intuitive, but worth talking about. Like why are those things often exploited? Why do we end up with events around those? Because they're useful. What types of classes do we end up with? SQL injection, buffer overflow, improper input validation, things that will lead to remote compromise and complete compromise. And so I'll touch on this, but Michael, I want you to weigh in on this as well. You know, one of the things we noticed as we were building this model, and it was also intuitive, but really only in retrospect, it doesn't make sense, I'll just go straight into it, it doesn't necessarily make sense to have multiple exploits for a given product of a given version, right? You really want to be able to have an exploit for a given target, and everything else that just reliably works, and everything else doesn't matter. Who cares? Because if it's patched, it's going to have all of those vulnerabilities, not just one.
Yeah, so this is something that the model struggles to account for, but when you think about it from the attacker's perspective, it's very intuitive. If I have an Adobe advisory with 15 vulnerabilities in it, and I know that I have a weaponized piece of code I can just hit up Metasploit for and use reliably against that version of Reader, why would I ever spend the time to write another one? I should just write it for a different version of Reader, for a different advisory.
Yep.
And so that's what ends up happening. Maybe 10 of those were really good candidates for exploitation that the model would predict highly, but it doesn't make sense to issue a prediction for them because an attacker would never spend the time to write it. So we're not the first people to think about this. I think we might just be the first to operationalize it, but Luca Oladi at the University of Trento published a paper at Weiss this year where he thinks about the work-averse attacker model. And he finds the same thing by looking at a completely different data set. He looks at the Symantec in the wild exploitation data set. I think it's called WINE, like W-I-N-E. And he finds that people rarely will exploit or write exploitation code for multiple things in an advisory. And that's because attackers only work on things that give them a payoff. And that payoff could be, I know this vulnerability can be sold for money, which, again, if there's something else that exploits that same version, why would anybody pay more for it when something exists? Or something that they could use to deploy ransomware or malware reliably and well, which means it has to be for a novel version. So the only exception, interestingly, is Internet Explorer, and the exception happens because it's so painfully easy to create Internet Explorer vulnerabilities that I think people just do it for fun, and then that also probably throws off our attacker model. But all this to say that there's a lot of academic literature about thinking about what do attackers actually do when they're writing exploits. And thinking about it from the attacker's perspective is actually what we're doing here. We're not modeling so much a piece of data being released about a vulnerability. We're trying to model, I have a bunch of vulnerabilities, who's willing to write an exploit for it? Is there a real threat for it? And if you start thinking about it that way, you can slice out a lot of the things out of the model that make it inefficient, like predictions for multiple things in a single advisory.
Yep. Great. And it turns out that in looking at the database, there were, these are direct results, and I think that these were the top 5 CVEs that popped out of one of the initial models. The number one thing that showed up was actually a vulnerability that existed in the wild, was part of BrickerBot, and was used as part of Mirai. And in fact, it wasn't even in our database. Why? Because it wasn't in ExploitDB. It wasn't in Metasploit at the time. And so there's a cleanup effect that you get by doing this, by going through the top of the results and saying, does this exploit exist? It just hasn't been categorized or named or numbered in one of the databases that we have access to. And so you can kind of see there's some really interesting IoT bugs that show up at the very top of the list. And Dulwich happened to be...
Let me jump in this
please.
code first. This is also really interesting about machine learning models. So what we learned for half of these is that we just had incomplete data. And that alone is a valuable consequence of building the model. We've talked about this for months now, where if the model is predicting things that already have exploits, that we then Google and find something already exists or it's already out in the wild, that probably means the model isn't bad. That means we have missing data and we need to import that data. And learning that information about our own backend systems is valuable for us too. Not as valuable as predicting actual exploits and then having them come out, but it's a consequence of, there's 2 ways to get bad results. You could have a very bad model or you can have very bad data. And if your model seems to be okay and your data is incomplete, then there's a feedback loop that naturally occurs there where we issue predictions, Cran looks at them, he's like, hey, there's already an exploit. We then go and update ExploitDB or we update Metasploit so that everybody can have access to that information.
Yeah. And in certain cases, there may not be a named vulnerability, an exploit that exists in the wild, but it's so easy to create them that we're just dropping proof of concept code for them. Dulwich, which happens to be a Python library to pull Git repositories and manipulate them, has essentially a command injection vulnerability, both in the client and also in the library. And so, we don't necessarily have to have an exploit in ExploitDB or one of the sources. We'll just write the exploit for it and release it to ExploitDB. I mean, there's a line there, right? Like if it's so easy, does that thing count as an exploit, or should we not counted as an exploit. So there's a spectrum, let's say. In this case, like, we'll just write it. So in that case, yeah, we added it. And we ended up with some other interesting highly scored CVEs. So sort of cherry picking out of this list of top CVEs, what do we end up with? Adobe Reader does show up in the list, though I wonder about this one because does it show up in the same fixed groups? We've certainly seen a lot of Adobe Reader CVEs this year. So maybe fixed group isn't exactly it, going back to that. Maybe it's like, maybe they're exactly, maybe, there are the people who update quickly and then there's everybody else. So I think we need to dig into the fixed groups concept a little bit more, but DLL hijacking and Snort, SQLi and Trend Micro, their control manager. Things that are relatively easy to exploit, lead to command injection, and are relatively widely deployed. And we definitely want to spend more time on the widely deployed bit. So with that, what are the constraints on the future? Jay, do you want to come up and give these slides? Can we have you come up?
We have a special guest to talk about the future because he's a man very familiar with it.
Yeah, so Jay is working with us at Kenna, is with the Scientia Institute, is somebody who's added a lot of value to this thinking over the last period of time, and I thought it might be useful for Jay to just kind of give a little bit of a insight into the future.
Sure, yeah, thanks. Hi, I'm Jay. I want to talk about this, yeah. So you mentioned on these, right?
Yeah.
Yeah, and so
that's fine.
Some of these things are really interesting when we're looking at how to look at the future. And one of the things that you guys have been talking about already is the current models are trying to look at how do we predict what exploits are going to have exploits published for them. In the future, we want to look at which of these vulnerabilities are actually going to be exploited. And so these are the things we want to try and limit. And so one of the first things that we realized as we're building these models and we're looking at the variables, and when we broke it down, we had about 300 variables on each vulnerability had about 300 variables about it. And what we found, if you look at this is showing essentially how much adding one variable into a model is going to add. And so at the far left, that first variable, when we add that first variable in, it was the most contributing variable, and it starts up just above 10,000. This is measuring in something called AIC. It's looking at the information in a model. But that first one, and that first model is there an exploit code published? And so our other models we're looking at, how do we predict if an exploit is going to be published? When we look at, is that vulnerability going to be exploited? That is the most important variable. The second most important variable, it drops the information helps the information in the model a lot. And that second one is basically what proportion of clients and how prevalent is that vulnerability out in the wild. And so that's a big indicator. But what we see, what's interesting is out of 300 variables, all these things that we can talk about, there are really just a handful of variables that are really important, that really help us understand, is this going to be exploited in the future? And as you get down into 15, 20, 30 variables, we're still getting some benefit, but just a little bit for each variable. And I think that's pretty interesting. We don't have to look at all 300. We can take sort of these top 5, top 10, top 20, and keep the model simple and not lose a lot of power in that predictive model. And one of the things also that we've been experimenting with is talking about probability. And there's a great quote from a professor who studies risk and probability. And he didn't understand why people found probability so unintuitive and difficult. And he finally said, after years of research, I figured out it's because probability is unintuitive and difficult. And so with this, what we're trying to do is we're trying to say, given a vulnerability, what is the actual probability it's going to be exploited? And so what we see is that most of these vulnerabilities are rated very low probability. They're less than 1% or so. We get up to here about 78% of the vulnerabilities are less than 1% probability of being exploited. And we saw that in the beginning, right? How many of these CVEs are there and what percentage are being exploited? And then about 2,400 vulnerabilities are predicted above 10% probability. And how do we know that these estimates, these probabilistic estimates are accurate, we create what's called a calibration plot. And what we have is essentially like when a weather forecaster says you've got a 40% chance of rain. 40% of the time it's probably going to rain. And you can actually record that over time and test that. And that's what we're doing here. So when we estimate a 10% chance of exploitation, we would expect about 10% of those to actually be exploited. When you get up into the higher range, you've got far fewer things being rated 70, 80, 90% chance of being exploited. But when we're saying that, it's 70, 80, 90% roughly chance of being exploited. But there's only about 450 vulnerabilities being rated over 60% chance of exploitation. But this type of thing, this is how we're going to ensure that the science is working, right? We can look at this. So perfectly calibrated is following that dashed line going up there in the little shaded region. It's a little hard to see. That's just showing the confidence that we have on different ranges. And so this is the future, trying to actually talk about, is this going to be exploited, and talking in terms of probability. And did you guys want to talk to this one?
Well, I'll do it.
Okay.
Yeah, I can start. So this is, at the end of the CNTA report, the very last slide that we show that Jay and Wade created is a measurement of all the dogmatic strategies that are out there for vulnerability management, or all of the kind of basic building blocks that we've talked about throughout the entire talk, and how they perform as a strategy for remediation. If you were to undertake a strategy of only remediating CVSS 10 vulnerabilities, is that a good idea? And the answer for CVSS 10 is that you will have efficiency that's about as good as random, about as good as throwing a dart at all of the 125,000 vulnerabilities that are out there. And your coverage, you will cover about 7.5%, is that right? It looks about right. About 7.5% of all the threats that are out there, all the vulnerabilities that will end up being exploited. But if you look at a strategy like, I'm going to pick a vulnerability at random from CVSS 7, or rather, a better way to think about it is, I will fix everything that is CVSS 7 or above. If you actually end up doing that, which is the size of that bubble in the very middle of the chart, I think that's about 30,000 vulnerabilities that you would have to remediate. Then you would have covered 55% of the threats that are out there. Your coverage is pretty good. And the efficiency that you had is about 33%. So 1 in 3 remediations that you undertake is actually remediating something that will have a successful exploitation or have an exploit published in the future or in the past. And that's not that bad of a strategy. I think that's where most organizations end up being today. They might have additions to it. They might drift it upwards by adding exploitability index or something like that. But if you look at all of the other strategies, none of them are that much better. You can remediate the top 5 vendors. You can remediate the top 10 vendors. That gets you pretty terrible coverage and even worse efficiency than random. You can remediate everything off the bug track list, and that does about as well as CVSS 7 Plus. It trades off some efficiency for some coverage. But what you see above is the actual in-production model that we use. And there's 2 interesting things about it. The first is that it has some concept of, do we have data about this vulnerability? But one of the data points that it integrates is it actually being exploited? Then you should definitely go fix it, which is why it has that almost 100% efficiency at the top. We're telling you to go first fix the stuff that we know has successful exploitations. And of course, that's cheating a little, but you want to be fixing them, and that's how we get that high efficiency. So if you want to remediate 20% of the threats that are out there, the best way to do that is just to remediate the ones that we know today are being successfully exploited. And that strategy will get you almost 100% efficiency with 20% coverage. I'll say one more thing, and I'll hand it off to you guys to rant about this too. We can all have insights about it. You could talk about this for the entire talk too, which is an interesting thing. So there's 2 things. The first is that every bubble that you see is a collection of vulnerabilities where if you fix all of them, you will achieve coverage and efficiency of this. But really what that is that's slicing the data in 2. Vulnerabilities that I'll fix and vulnerabilities that I won't fix. The value of the model isn't so much how good it is, it's rather that it's continuous. So if I know I've got 5 or 6 people remediating vulnerabilities, and they can churn out maybe 200 vulnerabilities per week, I want them to be highly efficient because I know I'm never going to get to high coverage. There's thousands of vulnerabilities out there. But if all of a sudden my CISO says to me, you need to cover 60% of the known threats out there, you can measurably say that would be an increase in effort of this much. I need this much more budget. I need this many more people. And that will take X amount of time. Yep. It's the continuity of the model that allows you to convert this kind of risk probability about vulnerabilities into a business decision.
It moves you to risk-based thinking, and it moves you to a place where you can make those trade-offs effectively. And in a world where Meltdown Inspector exists and side channel attacks exist, and there's more vulnerabilities than there is time, we have to do this. There's no choice. Everybody's already doing this, but we want to back it with science and give the ability for people to make good data-backed decisions.
Yep. And just to reiterate that, like if I go back to this one, if you've got one person fixing and remediating vulnerabilities, you want them to start way over on the right, right? Start the ones that are 90% have a 90% chance of being exploited. And that's what we're talking about in this chart. Essentially, you're going to start in the upper left and move down that curve going to 100% coverage. And I think that's really where the benefit comes in. And you get more benefit for less effort. And that's really the sweet spot, I think.
Got it. All right, we're going to go ahead and end it there. Thank you all very much for the time.